So as the gas, remember, the gas between the stars is really, really diffuse. And it has to go increase in density by a factor of 10 to the 23 to reach the density of the sun, right? Which is about that of water. So that first step in the process is these regions that just, for whatever reason, maybe there was a wave that went by, they became a bit more dense than their neighbors, you started forming molecules, and you get this runaway process that ultimately results in stars forming, and around those stars, in fact, planets forming. And if you think about it, these two parts, a planet like Earth, in fact, formed mainly from the dust in between the gas. Like what the Earth is made of has a lot in common with the dust. The Earth doesn't have a lot of hydrogen in it. And the stars, they form out of everything. Right? So the gas and dust between the stars form the stars and the planets. So we had some hints about where stars are forming from looking where there's lots of glowing gas, right? And it seems that young stars are always around gas, right? So that's a big hint that we saw from the images. And we'll think about how do stars form. And then some stars, they just never manage to become stars. And then when you make stars, well, what is left over from making the stars? So here's a picture of showing, looking across the spiral arm in the Milky Way, and we're kind of connecting how things work. If we look in other galaxies, and if we look in our own galaxy, a lot of the young stars are in these spiral arms. So we think that the spiral arms have to do where stars form. And in fact, what's happening is a spiral arm is a region of the galaxy where the gas is a little more dense. Now, if you remember, once I start the gas being a little more dense, it runs away on itself and makes stars. So what's happening here is gas flows through like this way, through this denser region of the galaxy. So this is early in the star formation process, and this is late in the star formation process. So you actually get to see the different stages of star formation from early to late as we go through here. So we have gas that's flowing in. The fact that it's a spiral arm compresses the gas. We start seeing the formation of molecules and the dust getting hotter. This is hot dust, hot dust. We're also seeing the dust getting thicker, right? So we see, even in these infrared images, that the dust is actually blocking the light. So in here, where actually stars are forming, how do I know stars are forming? Well, sometimes I see the little dots of the stars forming, but also this stuff is red, glowing red. That means the dust was heated up by something. It was heated up by the young stars in there. We might not yet see the stars. The stars are still stuck in the dust cloud, so we can't see them directly. Then as we proceed later in time, this cloud starts to dissipate because the stars are putting so much energy into the cloud that the cloud starts to spread out, and we're left with where we can see the stars forming through the gas and dust, because the gas is less thick. So we get this star-forming nebula, which is called Messier 17. So we know about this, and here's the before and after. Then, even later, these stars passed through this a long time ago, and you can see we have young stars here, and the dust and the gas has been pushed away from them for the most part, so we can see through it. So we have this sort of conveyor belt here, where this is the star-making factory, and here's the new stars rolling off the assembly line, and here's the raw materials coming in. The stars being made, here they're cleaning up, polishing them up, getting the dust off them, and then there's those new stars coming out the other side. So we can see the different stages. So here's, I mean, this is just a pretty picture. So this is another star-forming nebula where we could see the combination of the light of blue stars is being reflected off the dust. We aren't actually seeing the blue stars. They're behind here, and we just see the light coming back towards us. So we see this dense gas and the young stars associated with it. So how does star formation get started? Remember that the clouds get cooler and they get somewhat denser just because of how the dust works and the molecules work. But there's one thing to get a bit denser, but you really have to think like a star is 10 to the 23 times denser than what it starts out with. And even these dense dust clouds, we call them dense, they're about as dense as the densest vacuum that we can make up, not the densest. The least dense vacuum that we make on Earth could be like one of these dust clouds, right? It's 10,000 times denser than the rest, than the average, but it has to go from there all the way to a star. So what happens is if you remember, gravity is always attractive, and if you make it a bit more dense, the gravity can win out against what's holding the cloud up. What's holding the cloud up is the pressure, so the temperature of the gas. So as the gas cools, the pressure becomes less, and so the gravity can win out. Okay? So it starts to contract under its own gravitational force. The middle of that cloud is essentially, it's enclosed by all of this dust and gas, and as it's collapsing, it will heat up. And the center of the cloud becomes hotter and hotter until eventually it gets so hot that nuclear fusion can start in the middle of that ball of gas. And, you know, that's when you have a star. So that's basically how that's the basic picture. But how do you actually get that part of the dust cloud to begin to contract? Often it can have to do with other stars forming nearby. So another star forms nearby, it creates a little explosion that runs through the gas and compresses it, and that bit of gas, it was not dense enough to have the gravity take over, but it becomes more dense suddenly, and then the gravity just takes it the rest of the way. So you can have star formation triggering more star formation. So this is just showing that same picture of what we saw. This is schematically of essentially as the gas flows through, it forms these molecular clouds. You form young stars. Eventually, the gas is dissipated away. You end up with a young group of stars, and over time, they spread out and get bigger and bigger across the sky and eventually dissipate. So like the Pleiades is sort of a middle-aged group of stars. It's about 100 million years old. We identify older groups of stars and also younger groups. And we think that most stars form in these little clusters of stars, but over time, over billions of years, they get dissipated, right? They spread out. So this is showing what I mean by triggering star formation. Now we're looking in another galaxy, the M83. And if we zoom in, we could see tons of star formation on these spiral arms. And it's a bit chaotic, but it also kind of, you can see that there's regions where there's a lot more star formation, and you think that that has to do with, well, this type, the star formation here, actually triggered more star formation in the neighboring gas, right? So it goes beyond, it's a sort of nonlinear process that, that star formation going in one region can get star formation in neighboring regions to start. So what affects whether this actually works, whether the star formation happens, is that as the temperature of the cloud goes up, that cloud, for it to collapse, for gravity to take over, the gravity has to be stronger. So the cloud must be more massive to collapse. So if the clouds are typically hotter, the clumps that fall out of them and form stars will be more massive. If the cloud is rotating somewhat, right, it has to overcome the centrifugal force, right? If it's rotating, it's hard to pull itself in. So rotation will also make it need to be more massive to start collapse. And if the cloud, as you would expect maybe, there's magnetic field in the galaxy, and the clouds don't like to go across the magnetic field. So if you imagine there's some cloud sitting here on the magnetic field, it's not going to be able to collapse this way, because these field lines will resist it. It'll collapse down. So often spherical clouds become kind of pancakes. And similarly for the rotating cloud, it'll form it won't collapse as a ball, but they'll typically form a pancakey shape. So as we talked a little bit before, stars are often born in groups called clusters. Here's the Pleiades cluster. And these guys are super, super useful because all the stars are about the same distance away from us. They're all were born about the same time ago, and they're all about the same composition. So by looking at clusters, we see stars. The stars are different, but the only thing that's different about these stars is how massive they are. So some are bigger and more massive than others. So like this RG star is a star that's maybe a bit more massive than the others, and it's already consumed all of its hydrogen. Whereas these fainter stars here, they're at the same distance, so they must be inherently more faint, inherently less luminous. So that's why on your exercise, we gave you a particular cluster of stars, showed that data from a cluster of stars that's about 10 billion years old, but it's all at the same distance and the same composition. So where we were up to was talking about how stars form, and one thing that we see in the sky is that stars seem to form in star-forming regions. So then we expect a whole bunch of stars to form together, and then they actually stay together as they travel through the galaxy for hundreds of millions or even longer, depending on how big the cluster is. So our sun, for example, is 4.5 billion years old. We don't know which stars it was born with, right? There are stars nearby that are very similar in age to the sun, and maybe and in composition, and maybe there are brothers and sisters. I don't know, but you can look in the sky and find sibling stars, and some of them are bigger groups, bigger families, and others are smaller. And here's a small one, right? So this is, everyone knows what that is, I think, that picture. That is the Big Dipper. Now, unlike most constellations, actually Big Dipper technically isn't a constellation. There's a list of 88 constellations, and Big Dipper is part of a constellation. So when we talk about things that are part of a constellation, that's called an asterism. But it's part of the constellation of Ursa Major, and unlike most constellations or asterisms, these stars are actually associated with each other. Most constellations you look at, and it looks like there's 3 stars in a row, but one's back here, one's up there, and they just happen to make a pattern from our point of view. But if we look at the Big Dipper, this I think I just took with a digital camera. I think it even picks up that this guy's a double star. This is Mizar. But all these stars here, they're all blue stars, hot stars. They're O stars and B stars, and they were all born about the same time. They're all not very old, 10 million years old or so. And they all are the same age, and you can trace them back in time, their proper motions, across the sky, and see that they were all, at one time, much closer together. So this is called an OB association. It's a bunch of stars who were born together, and the only reason we can pick out these 5 stars or 6 stars is that they're still close together on the sky. They're all young, so they're all bright, and they're all about the same distance away. So this is a funny sort of one where we usually say, oh, constellations aren't actually, it's just from our point of view, and they aren't associated, but sort of the most famous constellation, which isn't really a constellation, are a bunch of stars that hang out together and were born together. So that's a family. Then it's called the Seven Sisters, by the way. No, this is the cloud. The Seven Sisters is another one. The Seven Sisters is an open cluster, which is the Pleiades, right? And I don't know, we saw a picture of that right here. Those stars are still very close together in the sky, and the ones we call the Seven Sisters are the brightest one of those stars, and they were also born all together, but longer ago. But it's a much tighter group than these guys, and those are called open clusters. And the biggest ones are the globular clusters, which can have hundreds of thousands of stars or millions of stars. And we've looked at pictures of those, and you've also, that's what your HR diagram was from last week for 47 Tuck. So in your tutorial, you'll work with an HR diagram for an open cluster, and I believe for the Pleiades, in fact, and a globular cluster for NGC 6397. So we know that the stars form in groups and these molecular clouds, but how does an individual star form? And what happens as it's forming? And what's the basic picture of what's going on? So within the molecular cloud, there are regions that are a bit more dense than the average, and their gravity starts to pull them in on themselves. So that's what we're looking at in the leftmost bit. It's maybe about 5,000 AU across. So keep in mind, Saturn is 10 AU away from us. So the size of the solar system are about much bigger, a few hundred times the size of the solar system, but much smaller than the distance between stars today, which is about 200,000 AU. So much bigger than this. That gas cloud starts to collapse, and because might be spinning a little bit, what will happen is instead of collapsing into a smaller and smaller ball, what you'll end up getting is a disk which carries the spinning part and a central spherical region which ultimately can become the star. So we have these two parts to it. The disk part is because the cloud initially can be spinning, and the central part is the actual, we call it a protostar, meaning it will become a star. And as this protostar starts as material piles up onto it, what it can do is drive an outflow up away from the disk, right? And then eventually we end up with a region much smaller. It's gone down by a factor of 50. But we can actually look at what's happening here, right? So we have this picture of a disk and then outflows up and down. And here's a particular example of a T Tauri star. So T Tauri star is a star in the process of being born in the phase where it has this disk and the jet. Now, in this picture, you might be tempted to say, this is the disk, but it's not. The disk is here. in the middle, and we can't see through it. It's because it's full of dust, right? And what we're seeing here is light reflected off the top of the disk, and then this jet coming out of the disk. So this is looking in a star formation region in the infrared. We can see what this process looks like, that we see this protostellar disk, as they're called, and a jet from the star. Okay? And they change with time, so we have a few pictures there. Now, if we look at the scale here, now we've collapsed from something 5,000 AU down to something not much bigger than our solar system, right? So you can see how we end up with two sorts of components here. Here's again more of these protostellar disks showing things on that scale of about 500 AU. This one is an amazing one, right? So here, this black line is the fact that we're looking almost edge on the disk, and it just absorbs the radiation through it, and the light on the top and the bottom is the light coming from the central regions of the disk, reflected off the gas and dust above and below. All of this modeling here, that's not real. That just has to do with how the image was made. You know, that would be a little extraordinary if it actually looked like that. So this sort of structure here is quite generic. We have other ones where we're maybe not looking precisely edge on, so we still have the absorption, but we can see down into the center looking at that protostar. So what happens to this the central region now? So the bulk of the mass is in that central region that is more or less spherical, and the problem is it can't just collapse straight down and form a star, because as it collapses a little bit, right? It collapses a little bit, it will heat up, and that heating up will keep it from collapsing further. So what happens is that this object, gravity wants to make it contract, but for it to contract, it has to lose energy in the form of radiation through its surface. So it's limited in how fast it contracts to form a star by how quickly it can emit radiation from the surface. So as it's doing that, what it does is it comes down these tracks here, right? These almost straight vertical tracks. It gets a little bit hotter at its surface, but the main thing it does is it gets much, much fainter. And what it's doing here is it's just radiating the gravitational energy that's released as it gradually collapses. Now, this shows a lot of information, right? So we have different masses of stars, starting at the top, 100 solar mass star, and along the lines are the number of years it takes to reach that stage. So 100 solar mass star is going to be a really massive cloud, and that means the pressure isn't very important. It collapses very quickly. It gets to this point at 10 to the 2 years, right? Just in 100 years, where it sort of turns. For the sun comes down here, it takes 10 to the 6 years before it turns, right? A bit longer, 100 times longer to reach, not 100 times, 10,000 times longer to reach, to become a normal star, right? So as stars become less and less massive, their evolution takes longer and longer and longer. And we saw a little bit of that on the worksheet, or gave a hint of that on the worksheet, but it even happens as the stars are being born. So let's look at a very low mass star down at the bottom. It takes 100 million years to go from a gas cloud and collapse into a star. And it just essentially, very gradually, its structure doesn't change by very much. Why does it stop collapsing? because eventually in the center it gets hot enough for there to be nuclear reactions. And that's what's happening right there with that lowest 1/10 of a solar mass star. As we go up to half a solar mass, it does almost the same thing, but and essentially takes 10 times faster to get there. Then when we look at the sun, it looks a little different, and I'll explain why it changes. So do you guys remember the structure of the sun? So the outside of the sun is doing this up and down motion called convection, and the inside of the sun isn't moving very much. It's the radiation carries the energy. So what's happening as the star comes down here, when it's very, very big in here, in the protostar, the energy is again carried by the motion of the gas up and down called convection. But in more massive stars, like the sun, eventually the inside gets hot enough that it no longer has to do this convection. And it forms in the middle now. The outside is doing convection. In the middle, it's just sitting there. It's hot enough that the radiation can carry the energy. So at this point here, where I put the arrow, that in the sun is where it starts to form this inside that is going to form the core of the sun. That region where it's not convective, it's just sitting there. Okay? Then it just goes along, and then this point, you see it hooks around. That hooking is when the nuclear reactions start going inside the star. And actually the nuclear reactions cause it to actually get a little bit fainter, and then it lands on that red line called the zero-age main sequence. And what that means is the star is now doing its nuclear reactions in the center, and the nuclear energy generated in the center is equal to the radiation coming out through the surface. So the star isn't changing very quickly anymore. What's going to drive its changing is not the change in its radius. It's going to be driven by it running out of fuel. So we're going to talk about that in a lot of detail this week. So that's why the different types of stars have different structures in how they go. So the more massive stars form this inner region where the energy is carried by radiation earlier, and as soon as that happens, instead of the star getting fainter and fainter, it just moves across the diagram, and the inside and the surface both get hotter and hotter and hotter, and eventually the nuclear reactions start to take hold, and then the star stops evolving so quickly. So if we look at the 10 solar mass star, it takes 100,000 years to reach the main sequence, and it will live as a star on the main sequence, meaning it consumes hydrogen in its middle, for about 10 million years. So 100 times longer. For the sun, it takes a bit more than 1 million years to reach the main sequence, and it will live there for 10 billion years. So the bulk of the life of the star is on this main sequence, but this is the pre-evolution of the star, before it actually gets the nuclear reactions going. So this thing called the Hayashi track are these lines over here, where the star is fully convective. The entire star is carrying energy by the gas moving up and down. Now, if you look down these stars down here, this track of being completely convective reaches all the way to the main sequence. So these stars, even when they're living and doing the nuclear reactions, they're always bringing new fuel into their middle. So these very low-mass stars, they take a very long time to get the nuclear reactions going, but like the one on the bottom, the 0.1 solar mass star will live for 1 trillion years. So 100 times longer than the sun. Okay, so we went all the way down to 0.1 solar masses, what happens if the mass is even less than that? The little clump of gas will have no idea whether it's massive enough to get nuclear reactions going. It might just, it'll collapse, and let's say it's less than a tenth, and it'll come down here. Let's say it's 8% of the mass of the sun. Guess what? That star will never get the nuclear reactions going. It will never get them going. And we give those guys a special name. We call them brown dwarfs, right? So our brown dwarfs are down here. These are actually just really small stars, right? And then over here, these are brown dwarfs. And they have different masses, but they're all about the same size. They're all about the size of Jupiter, you can see, in radius. But Gliese 229b might be a few percent of the mass of the sun, whereas Jupiter is about 1,000th the mass of the sun. Okay? But they're all about the same temperature. And these guys, these brown dwarfs, at some time during their life, they may have had some nuclear reactions, especially of the other things that are easier to fuse than hydrogen, like deuterium, if you remember from your tutorial last time, that deuterium really likes to fuse with other deuteriums and with protons. So these guys will have some deuterium fusion in their early stages, but then after that, they just cool until the end of time. And depending on their age, that will be what their temperature is, right? So the older ones will be colder and fainter. So that's different from a star. So a star like the sun, it'll sit there for 10 billion years, and it actually gets a little bit brighter over that time. These objects aren't stars. With time, they get fainter and fainter and fainter. And then we go all the way to Jupiter, right? So here's their temperature. Jupiter is only about 100 Kelvin, whereas a brown dwarf is about 1,000 Kelvin or in between. And we give them special classes, spectral classes. This guy is still a star, Theta 1. It's just a very, very, very low mass star. But you can notice it's maybe 10% the mass of the sun, but it's the radius of Jupiter, those very low mass stars. So if we go all the way down and we think about, so there's a distinction between a star and a brown dwarf. The star has hydrogen fusion going on. The brown dwarf never gets the hydrogen fusion to start. So it can have a short time where it seems to be stable for a bit, where it's fusing other things. But after that's done, they just get cooler and cooler. And a planet, what's the difference between the brown dwarf and a planet? So it really has to do with, it's a definition, right? And different people have different definitions, and we don't really, no one's agreed on it just yet. So as you go to lower and lower mass, eventually, when would you call it a planet? And generally, we think of brown dwarfs as being more massive than planets, maybe more than 10 times the mass of Jupiter. So if it's less than that, we call it a planet. Like I said, the brown dwarfs will have a period of when they had fusion going on. And then the third one is something that some people think of, but it's very hard to get the answer to this, is that maybe brown dwarfs form like a star forms by itself, whereas planets form in the disk of another star. Now, we don't know, right? Because we can't, when we see a brown dwarf, we can't tell how it formed. But you can imagine there's two ways of these things forming. And in principle, planets could form in their own clump too, but it wouldn't be a fun planet to be on because there'd be no star next door. What's nice about having them form in a disk is that they're right next to a star. So these protoplanetary disks, the disks from which these are the leftovers of forming the star. So we talked about the disk and the star forming in the middle of this rather massive disk. But once the star starts its nuclear reactions, it has enough radiation coming out to drive away a lot of that gas that was surrounding it. But a bit of that remains. So here's a picture of a protoplanetary disk. It's a T Tauri star. So one of these that is still kind of forming. And this shows what it looks like in the millimeter radiation. So it's the radiation essentially from dust. Oh, and it looks prettier, I think, when I shut it off. So this one's, it's pretty amazing. So you can see that the disk is divided into little rings. Do you see that? So I don't know how many rings there are. 1, 2, 3, 4, 5. There may be 8 different rings. And what we think is happening here is that what clears out this ring is a planet. So some object, maybe the mass of Jupiter or a few times the mass of the Jupiter, lives in each of those gaps. And what that means is the material that's nearby it gets kicked out by the gravity of that object. So by looking at the width of those gaps, you can estimate how massive that object is. So right here we're seeing a planetary system in the process of formation. It's much, much bigger than our solar system because of the angular scale here is quite large. So here we see the evidence of the youngest planets, that they're just forming, and they're forming when the stars form themselves, right? So this star is still in the process of forming, and we're already seeing evidence of the planets there. Now, if we want to look at finding planets later on, oftentimes the planet themselves isn't bright enough for us to see it. So how do we find that it's there? So one way that we find it is, this is an example where we have 2 stars orbiting each other. Those 2 stars, you know, one star will be coming towards us, one will be going away, and we'll measure the Doppler shift of all of those spectral lines. But if there's any additional objects in the system, those will add their own Doppler shifts onto the star. So in particular, you could think of a star with a planet going around it. If we look at the star, it moves back and forth in a little circle too, right? But the size of that circle is much smaller than the size of the planet's orbit, right? By the ratio of the mass of the star to the mass of the planet. So if you think of the sun and Jupiter, that's a factor of 1,000. Jupiter goes around, the sun moves 1,000th as much as Jupiter does. But we can measure that from the Doppler effect. So when we look at these stars later on, they've lost their disk, so we don't see the effect of the planet and the disk, but we can see the planet orbiting the star through the Doppler effect. The second way, there are other ways of finding the planets, is this rather simple idea that you can even do, an amateur can do with a telescope on the ground. So if the planet goes in front of the star, it's going to block a bit of the star's light. Now, if you remember that picture that showed all the stars coming down to Jupiter, Jupiter's mass is 1,000th that of the sun, but its radius is only about 1/10 of the radius of the sun. So when Jupiter goes in front of the sun, it blocks 1% of the light from the sun. I mean, we'll never see it unless we go further from the sun than Jupiter. But, you know, for example, when Venus goes in front of the sun, because it's so much closer to us, it blocks even more than 1% of the light. But if we're looking from a large distance, what we'll see is as the planet goes in front of the star from our point of view, the brightness of that star will dip, and we can see that once in orbit. So every time the planet goes around, we'll see this dip. Now we won't see this for all the planets, right? Because in this case, things have to be favorable geometry, that the star and the planet, that if the planet orbits like this, it will never block the star. It's only if it orbits in the plane that leads to us. Right? So, for example, if you think of a planet orbiting close to its star, it's much more likely that it'll block than if it orbits further away. You don't have to line it up so precisely. So this technique has been used to found most of the planets that we know of outside of our solar system by a mission where they monitored lots of stars to look for these transits called Kepler. So it found hundreds of planets. So what Kepler did was it just stared at a region of sky in the constellation of Cygnus, which is like the swan, which is a big cross that appears in the northern sky. And it's near the plane of the galaxy. So when you look, there's lots of stars to see in there. And it just monitored them and watched for these little dips very precisely. And it could get dips that were 1 part per 1,000 or even less. So very small planets around these stars. And it watched it for maybe 5 years. So even if the planet went around once per year, it would see it several times. So essentially, over the last 20 or so years, we've gone from knowing 8 planets which all are in our solar system, by the way, to all of those. I don't even know how many are there. And every day there's more planets discovered. So hundreds of planets. And we can see here so we have different sizes of planets on the vertical axis, starting from the size of Earth down here. And then the orbital period is in this direction. So 1 year is about here. So lots of these planets that we found have periods less than a year. And the reason is that these are easier to find because by that transit technique. That's our yellow picture, right? The yellow. And that's because if the period is short, the planet is close to its star, so it's much more likely that it's favorably oriented to block the star. So if we thought of a guy who's way out here, like this yellow one, it was very lucky that everything lined up perfectly when the planet is really far away. Okay? The other ways we can detect planets are from the Doppler effect, which I think are these blue guys. We can also find planets just by seeing them directly. So that we've done that occasionally, where you get a very high-resolution image of a star, and you can actually see the planet. So an example of that is around a star called Fomalhaut, which isn't very far from Earth. We can actually see the planet, except those planets are typically going to be very far away from their star, right? Because they have to be far enough away for us to see the light of the planet not being drowned out by that of the star. So if we look at what we think planets are going to be made of, here we have the mass of the planet against the radius of the planet. So how do we figure out these quantities? For example, if the planet is doing this transit thing, where it blocks the star's light, we can measure the radius of the planet, but we don't know its mass, right? If we see it doing the Doppler shift thing, we can measure the mass, but not the radius. So these guys here are planets where we've seen, but there's a third way to figure out the mass, but let's just think of the basic one, where the planet goes in front of the star, and we see the Doppler shift. We get them both. So we get the radius from how deep the transit was, and the mass by how much the star is wobbling. But usually we only get one or the other. And it turns out quite fortunate, in our solar system, there's lots of planets, right? There's not just one. If you have a star and you have more than one planet, if you have several planets, at least two, and you see the transits of at least one of those planets, you don't even need to see two sets of transits, the transit will be perfectly regular, right? But if there's another planet there, the transit won't be regular because the one planet will tug on the other planet. And sometimes the transit will come a little early, come a little late, and if you have more than one planet transiting, you can figure out the masses of all those planets, and you know their radius. So that's part of why we get so many of these things, right? So here you can see if we had different masses and different materials, so as the planet is more and more dense, right, the mass will go up faster with radius, right? So for example, if the planet is made out of iron mainly, so this is Earth here, represented in Venus, they're mainly made out of iron and rock, so they have a large mass for a small radius because the density is high. Over here we have some planets, two planets here, who are a little bit over 10 Earth masses in mass. The little, they're in sort of green. That's Uranus and Neptune. So they have the density a bit less than water, and that gives us a sense that planets that we discover way down here are probably like Earth in their composition, mainly rock and iron, solid. These guys, we think, are more like Neptune and Uranus. So they might have a central region with a rocky core and then surrounded by a lot of gas. And then if we go all the way up here, we have Saturn and Jupiter, and these planets, we call them, they're like Jupiter. They're mainly made out of hydrogen gas and probably not a large core. So the thing is if we were looking for places where there may be life, all of these are sort of interesting because, as we know from Jupiter, Jupiter has lots of moons that go around it that are rocky. So if you had a planet like Jupiter that was closer into its star, so warmer, hey, that would be a fine place to live. And so these objects down here are going to be 10 times the mass of the Earth, but the radius is just a little bit more than Earth. So if you were to live on them, probably it's rocky, but the gravity is much stronger than Earth. But, you know, you could adjust. Probably we could adjust, but some other creatures would adjust too. But so there's lots of planets have been discovered. And if we look at how many different planets as a function of size, so we have two things. So on the one, on the left is how many planets we have of different sizes and that have been discovered. And you can see that the numbers in each bar are numbers like 500. There are a few thousand planets that have been discovered around other stars. And there's several hundred over here who are about the radius of the Earth. So 381 plus 165 plus 55. So that's pretty darn good. In our solar system, we don't have planets in this size range, right? So it's between Earth and Neptune. And then as we go to larger planets, we don't see so many. Now over here, it's showing a different thing. So this is in each of the categories, how many of those size of planets are orbiting around every star. So if you were to add those all up, we have a third, and a third about. And what that's showing is that if we add up what's underneath all the bars, that tells us on average, every star has a planet. So there are as many planets out there in the galaxy as there are stars, or maybe a little bit more. And if we look, we go, what fraction of stars have a planet that's around Earth's size to twice Earth's radius? That's this region. And what that is telling us that half of the stars will have a planet of around Earth size. So Earth is not unique in its size. Now, not all of those guys are at the same distance from their star at Earth. They might be much closer, they must be much further. And what's important is the combination of how far you are away from the star and how bright the star is. There are a few objects that are at the distance from their star so that you can have liquid water on the surface. Right? However, for Earth, in fact, isn't at the distance from its star to have liquid water on its surface, believe it or not. We're a little too far. The reason why Earth isn't frozen is because of the greenhouse effect. So you have to be a little careful in thinking about it, but you have to be close to that region where we think water is on the surface. Okay? So Earth is a little bit cooler than that, if it had no atmosphere. But of course, Earth has an atmosphere. So the key thing is the planets form with the stars. They form quite naturally with the stars from this protoplanetary disk, and that there are as many planets out there as there are stars. Now here is a fun system which is called Kepler-62, which has a lot of planets. Now our solar system, let's just see, yeah. So it's showing the inner region of our solar system to the same scale as Kepler-62. The star in Kepler-62 is a less massive star than the sun, so it's less luminous. And we can look here, there's a green region. I have trouble seeing it, so I'm going to shut the light. If I have trouble seeing it, probably you have trouble seeing it. That's a bit better. So if we look at our solar system, that green region is the region where we would think the temperature is close enough for there to be water or that life could possibly happen. So in our solar system, we put that from the orbit of Venus to around Mars. And it goes a bit further than Earth because of this effect of the atmosphere. Okay? In this system called Kepler-62, a whole bunch, 3 of the planets are very close to the star, but 2 of the planets are in the region where the temperature is right for there to be water. And those pictures showing the colors, right? So what we really know about those planets on the left is the size. So we're showing their size to scale with Mercury, Venus, Earth, and Mars. And you can see that the 2 planets in the habitable zone, here and here, we don't know what their surfaces look like. That's our imagination. Especially this one, where you see like there's a continent and an ocean. We were very, very hopeful in polar caps. But the key thing is they're about the size of Earth. And they're living at the distance from this star, which is a red dwarf star, that is right for there to be water there. Now, Kepler-62, we're not going to visit it. It is really far away. It's in that constellation of Cygnus. It's maybe a kiloparsec away from us. But the reason we discovered it is that we could monitor hundreds of thousands of stars all at once to find an interesting system like this. But even in the neighborhood of our sun, we're finding systems like this.